Good morning. Can you see the screen? Yes? Okay, presentation mode, right? Okay, good. Well, good morning, friendly sharks and audience. My name is Paola Bandini. I'm a professor of civil engineering at New Mexico State University. I have been at NMSU for 19 years or a little bit more. I'm also the co-principal investigator of the Engineering Research Center for Center for Biomediated and Bio-Inspired Geotechnics, or CBBG. It's a National Science Foundation Engineering Research Center. And I'm thrust lead for infrastructure construction thrust in the center. So our technology is called Bio-Inspired Deep Foundation and Anchorage System, and I'm going to focus on the Bio-Inspired radially expansive pile. My team, just a second. What happened? Something happened. Let me go back. Okay. So my team, my research team includes my colleague, Professor Craig Knudson at New Mexico State. His specialty is in structural engineering and construction materials. And our PhD student, Ali Aleali, also at NMSU. And my specialty is geotechnical engineering. We are the team that developed and eventually was awarded a US patent on this technology that I'm describing. And the funding for our research that resulted in the patent came mainly from the National Science Foundation, through the Engineering Research Center for Biomediated and Bio-Inspired Geotechnics. In the last 4 years, we have received approximately $435,000 for research and experimentation, and we expect approximately $250,000 from the center, as well as some co-share from NMSU. But the Arrowhead Center has provided the financial support to for the patent filing, as well as the logistics and staff support. And we also they also awarded my student, and I was the faculty advisor, the participation in the Aggie I-Corps. So the technology that we have developed, or that we are developing actually, is the Bio-Inspired Deep Foundation and Anchorage systems. It has been patented, and it consists of a pile, a deep foundation that has greater load capacity than the conventional cylindrical piles that are used in practice. So the greater capacity comes from greater friction or greater shaft capacity. And that increasing capacity, load carrying capacity, comes from the expansion of the pile, which is something completely new in this in this industry for piles. So the Bio-Inspired radially expansive pile, or BREP, consists of a steel shell, a pipe that is split longitudinally, so it can move laterally. But it's first driven into the ground as any conventional, with any conventional pile driving equipment. But the two halves of the piles, or more, we could divide it even more pile parts, they stay together when it's installed into the ground. And then the split pipe is expanded laterally, radially, with an internal mechanism. And the two parts now, they are expanded and they are pushed against the soil, creating a larger radial pressure against the against the pile from the soil. That creates like an anchorage of our pile and produces or generates larger frictional resistance between the soil and the external surface of the pile. Of course, once that expansion is completed and locked, we can apply the structural loads, and the pile will develop greater shaft capacity and greater load capacity. So it's a pile that can carry larger structure, heavier structure. So this is just a schematic of the pile when it's expanded, and the expansion can be not necessarily on all the length of the pile, but in a portion of it. The expansion mechanism can be a core with a very high Poisson's ratio, where we compress the core, and to cause the expansion, we could the pattern include other mechanisms, mechanical mechanisms like scissor jacks or other type of jacks. And the pattern also includes the similar approach for soil anchors, but I'm not gonna include that today, but it's definitely part of the technology. So where does this idea of a lateral expansive pile came from? So we are, as part of this, the Center for Biomediated and Bioinspired Geotechnics, we look into nature, that nature has developed elegant and efficient solutions to geotechnical problems. And some of those are very complex in terms of expansion or penetration into the ground, excavation, load transfer mechanisms, like for example, the pads in catapults that serves like cushions, or the cementation of the White Cliff of Dover, where they withstand, the sands have cemented and withstand erosion and become very strong. So nature has those solutions developed, and we identify those strategies, those mechanisms, and adopt them in engineering solutions. And in other fields, such as geotechnical engineering, that has been used already. For our invention, we have used, for example, the mechanism of anchorage for penetration that earthworms use. They are imaginary earthworms. They are very soft, they don't have a skeleton. They are very tiny and delicate, but they are able to penetrate into the ground. How do they do it? Because they contract and expand their muscles, and by expanding against the ground, part of the body, they can provide, they can generate anchorage and the reaction that they need to push the front part of their body into the ground. And when they have advanced, they just relax the muscles and so on. So it's a cycle of this contraction and expansion, but the anchorage is what we are using. So razor clam, they also not only have a soft hydroskeleton, but they also have a bivalve rigid shell that is pushed into the ground. And we took that idea, that strategy for our split steel shell in our pile. So these are just examples of some of the strategies that we adopted for our pile. So why, why is this important, and why do we need it? Well, there is increasing cost for maintenance and development of infrastructure. And there is a large spending of, even though it's not enough, the federal government spends in transportation infrastructure more than $300 billion, for about 40% of that is in highways. There is lots of spending also in the privately owned infrastructure. even almost twice of the investment from the federal government. And significant portion of this spending goes in infrastructure that is supported in deep foundations, like bridges and buildings and almost anything that we think about is supported on foundations and piles. So there is also an interest and a need from the industry to improve the sustainability and resilience of the infrastructure. We see the applications of this type of piles on buildings and structures that are supported on deep foundations, like buildings that are 3-story or higher. Most likely they are supported on piles. Most bridges are supported on piles. Solar panels, solar farms, or transmission towers, for example. Transmission towers are especially interesting for our application because the foundations generally have to carry not only compressive load, but also tensile load due to the tension in the cables. And our application, I want to explain later, has advantages on that. And in those places where there are soil conditions that are not favorable, for example, when we have a very deep, the bearing layer or the bedrock is very deep, so we have to extend the piles very deep into the ground. That's expensive. It adds to cost and logistics and materials. Or whenever we have very large loads as well. So our technology works very well in compression and in tension or pull out, but and possibly also for lateral capacity, but we have to demonstrate that. Especially our application is very useful when in pull out and I'm going to mention later. So, but greater load capacity, and so that we need either less or shorter piles, or we can apply heavier loads. The need is for more cost-effective, large capacity and sustainable deep foundations. The market, it can be government and privately owned construction. However, I see that in private construction, the adoption will be easier or will go first, because if we provide, if a contractor can provide a more cost-effective solution, the owner will be more willing to want to use it. Right? So in places where the bedrock or the strong layer where that will carry the loads is very deep, wherever we have compression and tensile loads, and also for target expansion in layer soils. So if we have soils that are weak, they are compressible, but we have a layer that is strong. So to take more advantage of that layer, that stratum that is strong, we can target expansion on that layer and anchor the pile in that layer. And of course, there is interest, as I mentioned, in more sustainable infrastructure. If we if we provide a pile that is more effective in carrying load for the same dimensions and the same amount of materials, well, the technology will use less concrete, less steel. It will require less driving because it will require either less piles or shorter piles, and it ended on in being less emission per unit load or capacity. And we, as part of our research, we are working with a team at UC Davis and in the Engineering Research Center that to perform a life cycle sustainability assessment, comparing our expansive pile with the business as usual methods. So the competitors for our piles is driven cylindrical or prismatic piles that are or drill shaft that are the conventional methods. They have lower capacity compared for the same size or same dimensions of the pile. Taper piles that are like conicals that are driven into the ground, they are very good in compression because they push the soil against the sides and developing good frictional resistance, but they don't work in tension or pull out. Helical piers also are possibly a competitor. It doesn't require driving and fast. They are used in transmission towers and lots of the solar farms, but they are not applicable in all types of soils. So I want to show you some just selected graphs with some of the results just to illustrate the advantages. These are results from numerical modeling, very careful, calibrated numerical modeling. And in the graph, we have pile settlement, but in the horizontal axis, I have load, capacity, with the load that from the structure that the pile can carry. So the conventional pile is this line, this segmented line here with no expansion. And the other lines with the color symbols are different, are expansive pile, our technology, with different length, looking at different length of the expansion section, as well as different expansion pressure. Because we have optimized, we have looked at the effect of each of the, identify most of the parameters that are relevant and they are most important to optimize our design. And as you can see, the distance between the line of the conventional pile and the expansive pile, that distance represents the gain in capacity. So the more we move to the right, the greater advantage we have in terms of load carrying capacity with the expansion pile. And let me move here. I have another graph that illustrates also the improvement or the gain in capacity. So this ratio that I'm plotting here, the I, it compares the capacity for a serviceability settlement. So for that serviceability settlement for the expansive pile divided by the conventional pile, we know the expansion. So the larger the improvement index, the greater capacity gain in this case, for different expansion pressures. So you can see that even if we are conservative, relatively small pressure with a very short, only length of the expansion, until the bottom third of the pile, we can have an improvement of approximately 160%. Okay, just very conservative, just looking at that point. We are also testing, not only numerically, but also in the field. One of the facilities of our research center is at ASU, and it's a test pit that allows us to install mid-scale piles. It's a 12-foot deep test pit, and we had installed 5 piles, instrumented both in the soil and in the pile, 160 plus sensors. And this was the first series of the prototype tests. As you can see here, they are beginning to be embedded into the ground. And here the piles are already in place and are being load tested. So we have reaction being applying the load, and we actually measure how much the settlement versus the load carrying capacity of the pile. We learned a lot from this test. We realized that some of the expansion mechanisms, some of the fittings in the expansion mechanisms were not robust enough because we actually have piles that had more capacity than what we expected. But we learned significantly from this test, and we are already working on the next test series. These tests are proof of concept, and we demonstrated numerically that our expansive pile has a great advantages, and we identify the variables that are most important. And we are collaborating with the professor at the University of Waterloo in that component of the research. We conducted the first mid-scale prototype test in the test pit and gained experience in the load on the pilot test instrumentation, and we identified the features that we need to redesign in our next stereo test that we are preparing for and plan for spring or early summer. We are actually planning for 2 series of tests with 2 different ideas for the expansion. Also, we have plan and funding from CBG to perform centrifuge test, and another CBG test-bed facility at UC Davis. This is the largest geotechnical centrifuge in the United States, and the testing will be done in 2022-2024. And the next steps also include the development of the design methodologies eventually can be implemented in the field, in practice, and also expand our work to develop the bioinspired expansive soil anchors.
Dr. Bandini, I hate to interrupt you, but just to make sure we have time for the next 2 presentations, okay. Just want to keep an eye on the clock here real quick and just see if there's anything you'd like to wrap up with here before we pass it over to
our commercialization path is licensing the technology to the contractors, the specialty contractors that work in installation of piles and soil anchors. We have industry partners in CBG. These are all their logos, and so they have the first option for licensing. And after that, we can go to other contractors, and we want to partner with industry for to advance from the mid-scale to the field scale test. Thank you.
Excellent. Thank you, Dr. Bandini.
Yeah, sorry that I went over. Thanks.
No, not at all. Well, it was a great presentation. I just want to hand it over to our friendly sharks here for a couple quick questions.
Okay. Sorry. I should actually share again.
I have a quick question. When this is commercialized, will you have to have a lot of instrumentation in the piles? I'm just wondering if there's ever a risk of, the pile, I guess, breaking during the expansion or the expansion not being uniform, so that over time it compromises the integrity of the pile.
Yes, well, the pile is made of steel, and we can actually determine the steel strength and thickness that is needed. Also, there will be pilot tests to demonstrate that it can be done in the field. The piles itself, once the design methodology has been developed and it has been demonstrated in the field, the pile itself doesn't need to be instrumented. It doesn't need to be, so maybe during the research stage, it will be, so we can monitor and learn from the installation. But once the technology is commercial, it will work exactly as any other pile. Once the expansion is, we reach the expansion needed, the expansion is locked, and then it remains fixed. So there we are considering like filling the pile with concrete so that it will not retract.
Okay, thank you.
Mm-hmm.
I understand you're engaging in at least one partnership, maybe multiple right now during the still the development process. Once you are in a stage where the technology could be commercialized, what will you do? Will you license it out and get a royalty, or will you still partner with somebody and do it together, or will there be a spin-off, or what are your plans?
I believe we are gonna, we are in agreement. It's licensing is the ideal. Okay. Because the best industry to the best agency to carry out to sell the put it in practice are the specialty contractors that they have the experience, the equipment, they have, they want to, they are eager to have new technology to sell it to their clients. If they can offer a competitive technology that's more cost effective, that gives them an edge. So they will be the ones licensing that.
Great. Thank you, guys. Thanks to the Sharks. Thank you, Dr. Bandini.
Thank you.
Our next presenter is Dr. Hojun Lim from Sandia Labs, who will be talking about revolutionizing manufacturing through machine learning.